Well, you're going to record me too.
Yeah.
All right.
You're part of the
Couple of quick announcements before we get to our guest speaker this evening. Our speaker is Mr. Jeff Delmas, and Jeff is our observatory director. He's been in the process of upgrading our 21-inch direct with a direct drive. He's going to talk to you about it. This has been a multi-month project. They've overcome a lot of problems. We're on our way to becoming a research-grade facility. Jeff's doing that for us. You probably haven't seen my face before. There's an announcement that goes with that. Our president, Don Martin, has retired, and our vice president, Michael Buford, has moved up, and I got appointed to fill in the remaining term of the vice president. Yay! Yay! Good job! Yeah, right. So I'll be your host for the evening. We have one announcement that has to do with the facility. Frank?
The handle broke off the toilet. Took the top off the toilet tank. Look there right behind the handle and just pull up on the lever from inside the water tank, and it'll work. We'll have a new handle tomorrow night.
And wash your hands.
That's on the claymore. I don't think we have any other directors. Is there a planetarium director announcement?
Really, the main thing we've got happening is this weekend we're doing some maintenance on our vintage projector here, our Spitz A3P projector. We've got one of the few people that actually work on it coming into town this weekend to do some maintenance on it. So just to keep it running, because it's from about 1963, so we want to keep it going.
It'll probably look a lot spiffier next time.
No, it won't. It'll look about the same. Just maybe a little less dust.
Yeah, but it'll work better.
It'll work better.
Hopefully. All right. I don't think we have any other announcements, so without further ado, Jeff, would you like to come forward?
Hopefully.
All right, thanks. It's good to see everybody here tonight. Yeah, what I'm talking about is the Swanson direct drive system, and I think I do need new batteries in my.
That's okay. Okay. I'll
Just say clicker and we'll click it.
Good.
I wondered about this because
yeah, I have to click it from here.
No.
Uh-oh.
He says it comes back.
Oh, it does come back.
You don't want us to just click it.
I want to watch the
Test it.
And that's
Okay.
Yep.
Yay.
There it goes.
All right.
Okay, just a little about me. Yeah, currently I am the observatory director here, and I am not a professional astronomer, but I am a lifelong amateur astronomer. And I even made my own 10-inch telescope back in the early 80s. I was nearly finished with that telescope after about a year, and then met my future wife, Deborah. She's right over here. And then it took me another year to finish. Let me tell you a little bit about the history of the Swanson. It's named after Conrad Swanson. He was actually a founding member, and he was a professional astronomer who worked for NASA. It was the observatory was completed in 1956, and it was the first and only building up here when it was finished. And that's the domed building just to the south, connected to this, really. It originally housed a 16-inch telescope, and that's important to remember. I'll tell you why later. And it was purchased from a maker in California, I think for like $800 or something. It was a sizable chunk of change back then. But in 1960, the Society approved a proposal to construct a larger telescope, which is the telescope, the optical system that we have today, the Swanson 21. And I don't know the exact date it was completed. I really should have done a little more investigation, but I know it was operating by 1965. The scope originally had a clock drive, which is just a simple motor that would rotate the scope westward 1 revolution per day as the Earth rotates eastward 1 revolution per day, and thus allow the scope to track the stars. So there's a picture of the original 16-inch telescope with Dr. von Braun and Ernst Stühlinger. And you can see the little clock drive. Somebody the other day said, told me that they saw a telescope, a large telescope that was being driven by an old sewing machine motor. And it kind of looks like an old sewing machine motor right there. But that's the original 16-inch on the pier that exists today, in the dome that exists today. In the early 2000s, the Swanson was upgraded to have motor drives on both axes. It actually went through a couple of iterations prior to that, but I don't know much about that. I affiliated with the society in the late 90s and was here during this upgrade. And it was the first time that we were able to computerize it so that then we could operate it from the control room downstairs. The control room actually used to be a dark room, but nobody does film anymore. It's all electronics, so we didn't need a dark room. I don't think that dark room had been used in 20 years or more anyway. But we had a number of problems with the system. Tracking had what's called periodic error due to quite a number of gears that were involved, and limited us to about a minute for a single exposure. If we were lucky, we could get a good minute. And slewing from one target to another was quite inaccurate. We typically had to star hop, and we actually had to have a what we call a finder cam, a wide angle camera that would look at about 20 degrees of sky so that we would know where we were. And then we would kind of move over to a known star, resynchronize the computer, and then go to our target, which you couldn't really see with the finder. Another odd problem that we had was the bottom of the scope would hit the mount when near the zenith. And as any observer will tell you, the best viewing is near the zenith because that's where the least amount of atmosphere is. And, you know, the lower to the horizon you get with your telescope, the more atmosphere you're looking through, and thus the more dust and stuff you're looking through. That's why the sunset looks red, but overhead it's nice and bright. Bright. What color is it? It's 5,000 Kelvin roughly. White or yellow. We tend to draw it as yellow, but it's white. The system as a control system was an open loop system. The only thing the computer knew about were the it could tell the motor how many times to turn. And we had clutches, and if you moved the scope through the clutches by hand, which you know we would avoid doing, of course, but if for some reason you did that, then the computer completely lost track of where the computer had no idea where the scope was pointed. And the overall system was very finicky. Resulted in operators having to learn to deal with inaccuracies and limitations, and it really made it hard to operate. And very few people really could be trusted with operating everything. every aspect of it. So another goal is to simplify and harden it, make it much easier to operate. So here's a photo or a couple of photos. That's the scope, of course, and this is on the old mount. I've got part of the old drive system. This is the declination drive, and I've got it now set up as a museum piece, but we don't have power over here. But we can plug it in later. And you can see how the worm gear moves you can see that worm gear over here on the declination axis. So that's the declination axis, and then that's what's called RA, right ascension axis. And they are at 90 degrees to each other. So there's the complicated gearing, and I thought about bringing that down here, but it's very heavy. That gear subassembly, it's very heavy and quite cumbersome. And I've got the observatory open, and after the presentation, if you're interested, you can come up and take a look at the scope live. We won't be viewing tonight because there are clouds out. But you can imagine kinds of errors that could be introduced with a complicated gear system like that. And here's a picture of Logan, me, and Tom Darrington with that little blue cylinder, looks kind of like a soda can, is the camera that we use. That's the main camera we use. We have other cameras. It's a CMOS camera, basically a video camera, but we can do long exposures with it, and it'll stack up the video frames into one single image. In effect, the telescope is a camera lens. Are there any camera buffs? Anybody who's really into camera stuff? Not too many people are into cameras anymore. But as a camera system, our Swanson 21-inch, and when I say 21, it's the diameter of the mirror. As a camera system, the Swanson is a 2100 millimeter f4 lens. And that's the camera body, that little blue cylinder. So here's an example of the kind of error we got that we would have. You can see stars are kind of elongated. Actually, there's an out of focus problem there too.
It looked like popcorn balls.
Yeah,
Yeah.
not very good. Oh, and one of the main things is we did 30 images that night, 24 were bad, and we got 6 good ones. That was not typical, but it wasn't that unusual. I mean, we would often take, 30 to 50 images, and half of them would have problems. So like I said, we wanted to improve. Got a mouse somewhere. Oh, that's that. Improve tracking, slewing, simplify the operation. In short, bring this up to a research grade instrument. It's a nice telescope if we can only control it. So we embarked on an effort to come up with a new system. And any engineer will tell you the best way to fix a fault-prone component is to eliminate it. So we eliminated all the gears, no gears. We have what's called a direct drive system where each axis is attached directly to the rotor of a large electric motor. And the electric motor is a very high torque, very highly controllable motor that can go at any speed we want it to And we wanted to go slow. We wanted to go 1 revolution per day, most of the time. And then when we want to move it, we want it to go like 5 degrees a second or something like that. Then rather than relative position encoders, we decided to use absolute encoders. Those are, so we put the encoders also, they are attached directly to the axes of the telescope. So the computer always knows, no matter whether you push it by hand or if the motors move it, the computer always knows what the scope is pointed at. So we never lose position. And we used a control system from a company called Sidereal Technologies. That's what we had used before. We were familiar. It's a small company in Oregon. And the guy who started it is very helpful. We've used a fair amount of his time, actually. The control system is a closed loop system, meaning that basically the controller will tell the motors, go this far, and then the encoders will feed back the position and say, hey, the scope is really here. Whether you told the motor, whether you told the motors to go to this place or not, here's where the scope really is. So then the control system can adjust the amount of power and torque needed to control that telescope. So we made a proposal to the VBAS Board of Directors in June of 2019, and the board approved an initial layout of $13,500. It was not enough. We had to go back to the board and ask for an additional $1,500 a bit later. So once we got approval, we spent over a year in pure engineering, where we were designing parts, selecting components, then procuring them and getting parts manufactured that we had to get manufactured, and kind of planning how we were going to disassemble and assemble things. This is just the first page of the design document, and then the spreadsheet basically showing the major components that we were looking at. And we had 2 options, and one was a high precision option that was going to be double the cost of, so I should say an ultra high precision. And we realized we really did not need the ultra high precision, because our scope was going to be subject to things like wind and other things that were beyond the control of the control system. I want to take a few moments to recognize the engineering team. So the original concept for the direct drive system was made by Wes Swift. He was the previous observatory director. I was hoping he might come here tonight. He's had some health problems, and he's not been out here too much in the past few years. He is in one of the videos I'll be showing. I think he's in one of the videos. I've got a picture of him. As I assumed the position of observatory director, I embraced this and kind of took it on to and committed myself to making this a reality. And I took the role of project lead and did most of the mechanical and system engineering with review and input by other team members. The full team is me, Mimo DiMartino. I'm sorry Mimo's not here tonight. I got to say, it's been, he was definitely co-leader on this thing. We worked really bouncing ideas off of each other quite a bit, and much of and he did a lot of the manufacturing of steel components, because he's gotten pretty good at welding. And so we've got some steel components that we had to manufacture. Logan Curtis, Logan's here. Raise your hand, Logan. Yeah. So Logan did a lot of mechanical and software engineering stuff, and Logan is, I would say at this point, he's the primary operator. He knows more about operating the scope even than I do, and I trained him originally. Now he has to train me. And Chuck Lewis, Chuck's over here. Chuck came in really about a year ago, right? Year and a half. I couldn't remember when it was. So he came in at exactly the right time because we were just getting ready to start doing all the electrical stuff. And I have to say that, so Chuck put together our power distribution box, and we've got, what is it, like 4 power supplies in that thing, and we've got to, route power and data around, and so Chuck put all that stuff, made it all fit into a box. We mounted it up. It's the only subsystem that worked first time out of the box, so to speak. So hats off to Chuck. And Tom Darrington also. Tom couldn't be here tonight. Tom,
In fact, he snuck in behind.
He snuck in.
He snuck
Snuck
in.
in.
behind you.
You said I'm coming late, didn't you?
yeah, well, okay. So Tom contributed in a lot of different ways, and he's the kind of guy who, as me and Mimo, or Chuck and Mimo, or me and Chuck and Mimo would, mull over some problem, Tom would be off to the side, and all of a sudden he'd say, I think if you switch that red wire with the blue wire, and we go, oh my gosh, that's it. And then, of course, Wes Swift provided concept on this thing and did a review of the documentation and engineering. And we got him up right when we began testing. We also had lots of consulting support from Dan Gray of Sidereal Technologies, as I mentioned before. Is it? It's not wanting to advance. That's weird. So there's a picture of everyone. Okay, come on in. We really didn't track the hours that were put in on the project, but I've conservatively estimated that together we put in over 1,500 hours in design, engineering, and construction. And add to that the hundreds of emails, phone calls, numerous lunch meetings, and it all adds up to a lot of volunteer effort that's been put into this project. I also want to mention a latecomer to the team, Chris Matson. He's here. Well, raise your hand, Chris. He's a control systems expert who works with Mimo and came in to help us with our PID settings, and I'll tell you a little bit more about that in a bit. But thanks to him, we're operating much smoother than we were just a few weeks ago. This is the control computer from Sidereal Technologies, and as I referred to the three-letter acronym PID, it's proportional integral derivative, and it's a kind of a standard control system used a lot in industrial controls. And in our case, the feedback is angular position for each axis. These are the motors. These motors, the rotor and the stator together weigh, I believe it was 34 pounds. So these things, and You might not believe it, but the heavy part is the part that goes inside. That is the permanent magnet part. And then the electric windings are in the stator. Yeah, electric motors have two parts, rotor and stator. The rotor rotates and the stator is stationary. And these are the absolute encoders. They're 24-bit optical encoders on a 300 millimeter diameter ring. That's roughly 8-inch diameter ring. And you can see this is the edge of the ring. And that's kind of a little barcode. And then this little guy is a camera that monitors that barcode and knows exactly where the ring is in angular position at any time. And here it is mounted. This is the RA axis and then the deck axis. So the encoders have to be real close to the motors to make sure there's no twisting of the axis that would cause incorrect feedback to the control system. This is a CAD model. I'm actually going to skip. I was going to do a demo of that, and I can do that later. But neither the motors nor encoders came with any mounting hardware. They are sold frameless, and by frameless that means there's no frame to mount them yet. So we had to design the mounting frame and the mounting support system and all that stuff. And let's see. Yeah, total of 59 parts were designed and manufactured to achieve, to get a complete system. It doesn't look like 59 parts. This is the assembly. This is actually a 3D CAD model, and I could open it up and we could spin it around and all that stuff. But you've probably seen 3D CAD models before. If not, we'll take a look after. And we wanted to get all the parts manufactured before we started disassembly, because we didn't want to have to all of a sudden find out that, oh, we can't get this part manufactured for 3 months and keep us from being able to work. So that's why it took a full year in design and manufacturing to before we started disassembly. In addition to that, we had to manufacture or modify a few parts during the assembly process when needed changes arose. In the end, we had over 40 drawings, many with multiple sheets. Yeah, I'm not going to demo that for the sake of time. Here's some of the drawing sheets that we had. So you may wonder who manufactured these. Well, we had 2 volunteers, 2 companies volunteered to help us out. We got pretty good at manufacturing, working with steel plate and steel sheet metal and aluminum sheet metal. And we were able to manufacture most of those things, but we got help from a company called DRM Controls of Lawrenceburg, Tennessee, and then Teledyne Brown Engineering here in Huntsville. These are the new bearing foundations that we made. And I wanted to point out, so this is the north bearing on the left side and the south bearing. You can see both on the right picture. But the north bearing, you can see we can use those screws to lift it so we can go up and down. And then we've got screws on the side, and we wound up putting 2 screws on each side. And that gives us left-right control. So this is how we do polar alignment. So we can, we've got 2 degrees of freedom on the north foundation. And the old way, the way that it was done before, was simply by using shims. So they would have to, yeah, it was not good at all. I mean, you know, it was, that's what they had, that's what they did, and it's fine, it worked. But it was not easy to adjust. And Chuck and I did the polar alignment using a piece of software. What was the name of that? SharpCat. Yeah, and boy, that was a breeze. And we came in within less than an arc minute. I don't remember exactly what it was, but it was really good. And DRM made these components. So these are all aluminum components. And the hubs, the small rings, those are the most complicated. You can see there's lots of holes in them. And because we made one hub design and then used that for both rotor attachment and encoder attachment. That's why we wound up needing 4 of those. And DRM is a company that Lonnie Cooter bought. Lonnie actually used to work for, I can't remember the name of the company he worked for, but they supplied factory automation control system equipment. And DRM is a company that makes factory automation, like factory assembly line type stuff, you know, automated lines.
The robotic arm, whatnot.
Yeah. And so he used to be a supplier to them, and he's done a bunch of telescope stuff for them in the past, and he went and asked them to help out, and they were glad to. So they manufactured and donated all the material and manpower for those parts. So we didn't have to pay anything for those parts. Teledyne Brown also contributed, but they've got a legacy of contributing. In 1960, they designed and manufactured the truss tube for the Swanson and the mount, well, what we call the weldment, the thing between the 2 foundations, basically the mount that's on the pier. And so they agreed to carry on that tradition and help us out. And they also donated all material and manpower, or human power, to get the parts made and to us for the encoders and brakes. The encoder ring required mounting on a conical stainless steel disc. We couldn't use aluminum for the encoders because we had to match the thermal expansion coefficient of the ring itself. And they said, well, you can make it out of any material that matches these values. Well, the only practical material there is stainless steel that matched the, well, that's what it was, that's what the encoder itself is made of. So that's what we made it. Now, here's an old drawing from Teledyne Brown. I brought that drawing, it's up here. We can take a look at it afterwards. I wanted to zoom in on the title block here. And you can see it was, I believe it's February 11, 1960. I think that's 2/11, maybe a 1/11/60. There's a, yeah, 2 February. Yeah, February 2nd. And then the engineer signed off on it on that day. So 2/11 is when the engineer signed off. The draftsman completed it February 2nd. And they didn't have spell check back then, unfortunately. And this is the southern pronunciation, I mean, the southern spelling for mirror. I think it's actually the Texas spelling. So here I am with Mitchell Holman of Telenon Brown. He was my contact there. And these are the two stainless steel discs that they made. Those were the only parts that really had to be made to very tight tolerance. I just want to warn everybody, if you ever do a complex mechanical project, double your fastener budget, because well, we wanted to use all stainless steel because we had trouble in the past with, non-stainless fasteners rusting on us and even failing in some cases. And the rust will drip, will fall down and stuff like that. In cases where stainless steel was too expensive, we tried to use galvanized fasteners. November 27th, 2020. That is, oh yeah. That's the day we started disassembly. We originally planned for a team of 4 to 6 individuals working, pretty much every weekend, 1 or 2 days a weekend, and getting it all done in 3 to 4 months. Yeah, it's not funny. But COVID changed that, and we limited the number of people to 2, and every now and then we had 3 for quite a while. And of course, trying to meet every weekend, that didn't work out. So it was inevitable, it was going to get stretched out. In addition to the operational parts that we manufactured, we had to manufacture, we had to fabricate quite a few custom tool and temporary support systems. And I've got one of our favorites here. Nemo made this. It originally started out as a gear puller, and it had like 2 pieces here that we could clamp over the gears and then pull them out because they were stuck to the axes. But then it turned into a rotor insertion and removal tool, and we still use it. I mean, we can still use it. We're going to keep that tool around. Remember, I mentioned that the back end of the Swanson would hit the pier. Well, and that's the wedge of sky that is ideal, that we really want to use. And we couldn't figure out why did they design it and allow it to hit the pier. Well, they didn't design it that way. They built the pier out of its concrete, so they weren't going to change it. And originally it was a 16-inch telescope, and it had plenty of clearance. Then when they put the 21-inch scope on it, they just didn't bother checking that, I guess, or fixing it. So we realized that we wanted to address that, and we figured out that we could simply lift the RA axis about 5 inches, and it would give us all the clearance that we needed. However, when we lifted the RA axis, we found that the top of the scope interfered with the dome. The top of the scope hit the dome, the top of the dome, not the side, just the top, because the scope is mounted above the center of the sphere. So what did we do? We lifted the dome. Yeah, and I'll show that. So what we worked on is a legacy system. We had to take it as it is. You have to take it as it is. And you never know what problems lurk ahead dealing with the legacy system. And I got to where I was telling people it's like running a hurdle race blindfolded. And each hurdle is a different height. And we don't even know how far apart the hurdles are, and we don't know how many hurdles. So we would, take a few steps. We take a few steps forward, find some seemingly insurmountable issue and say, okay, let's stop for a while, think about it, and figure out what to do next. It's very different from designing and constructing a system from scratch when you've got, blue sky to deal with and you can just design anything you want. But we love our historic scope and have high hopes for its continued use. Consider, for example, the counterweights. So the counterweights originally were at the connected directly to the deck axis. So the scope is on the left side of that. We call this the weld lint. And the scope's on the left side. In order to balance it, we have to have counterweights. Before we mounted this telescope and the counterweights, we had kind of a dummy. We had just the motor and the encoders up there and a dummy weight to balance it. And we ran our control system and everything was running smoothly. When we mounted the scope and the counterweights, we found we were having lots of problems. And Dan Gray at Sidereal said, "You've got a mechanical problem. I'm telling you, the rotor is colliding with the stator." And we thought, oh, what? We'd already checked that. And no way, that's not happening. So then we realized that the weights that are the counterweights were actually bending the axle enough to cause the control system to fail.
And how do we test for that?
Yeah, so we confirmed that by dropping that, by dropping the counterweights down to minimize the bending on the axle. And then we tested again and the control system worked. So we knew that the problem was the bending. So then we knew that we had to offload the counterweights from the deck axis. So we had to design and get these constructed. And luckily the counterweights fit exactly on, I think it's 2.5 inch nominal pipe, galvanized pipe. 2.5 inch nominal galvanized pipe has 2 7/8 inch diameter OD, outside diameter. And the threads that the counterweights have are 2 7/8 dash 16, was it? It's very fine threads for 2 7/8. Yeah, 2 7/8, 16 threads per inch. Yeah, Chuck.
We should probably point out over in the left-hand panel there, the 2x4, even with all of the sophisticated
Yeah.
hardware that we have.
That's our support
The
system.
2x4s and ropes came out to be the heroes of the day.
Yeah. So here's the finished scope with all new direct drive motors and absolute encoders. There's Chuck with the completed scope. Just posing for a picture. Couple of other close-ups.
Is it working?
Yeah. That's what I'm going to get to now. So I'm going to show a few videos here. Uh-oh. Okay, this is November 27th, 2020. I'm sorry, I kind of messed that up.
These are available
I've got to.
YouTube.
So we I'll tell you when it comes out. Okay. So that's that one. Then December 5th is when we took the weldment down. So first we had to move the OTA over and get it off the lift table. Okay, so now we're open stuff. Didn't come off. Oh, I got that. Order off. That's the order that's in here on the thing. Support system at the top of the dome, from which we hung the chain line. This was one of the days we had three people. Lower this thing. Got to get it down on okay, finally it's down. We're having a little trouble getting the north end where finally got it moving.
Okay, well, we're finished for the day and we've got the weldment off the axes.
I just wanted to tell you, you can go and see all of these. If you go to our society YouTube channel and look under playlists and view the full playlist, there's a total of 27 parts there. I'm only showing clips from a few of them tonight. One of the things that we had to do is that the motors came, rotor separate from stator, and the rotor is a very powerful magnet. You can't get any metal close to it. And you can't just construct the rotor into the stator and you have to build that gear. Logan even did some 3D printing of some gears. He actually got it on the belt pad, doing all of the gears together. You can see this one. So this is the partially part. This part, we have to come up with And that gear hub on the deck axis, it would not come off. So this is where the RA, or the both the deck and the RA axis. Even letting, the TV blaster, there's TV blaster right there. And that would not really hit it. We had to use far more.
Okay, well, we successfully pulled off both the south.
So after getting those off, we smoothed the axes with sandpaper, basically smoothing off all the burrs and everything. Okay, now we're mounting motors in the weldment onto the pier. And now we're up to May of 23. We started in November 6 months later, and we began to assemble everything. Well, we hit a problem here. These are half-inch diameter bolts, and somehow or another so start working on it. That's what all three of us working on that, working on it. No, it's not going to go anywhere. So yeah, cut it off. We have to cut it off. We not actually know that in the last find out what happened, and we had cross-threaded somehow. We had 18 good bolts. So we got we had to drill some holes for the encoder mount. We had some of the encoders. Yeah, this is one of the longer videos. I'm sorry? But we planned each session, you'll see, if you watch this whole video, there's an introduction on each one. There goes the weldment up on the foundation. And here we're just putting this wooden thing so that we can, that's another thing we had to build, something to balance the motor. And so that is just enough weight to balance whatever weight is on the
Well, we're done for the day, and everything
opposite side. I'll show this one real quick. It's kind of boring, but so Chuck and I, the tolerances for the encoders are extremely tight. And you can see that little dial indicator. So that measures from 2,000 to the inch. And so the monitoring Okay, we're finished now with now it's time, so we've got, at this point, it's, October 24th, 2021, 2021, October 24th. So it's taken quite a while to get to here, and we're allowing them to but we're also testing some software on this today, and Michael, at the end of the each one of us is kind of working on a separate thing, and all of this pieces completed. So Logan's over here in the background, he's at the computer, trying to check some things out. And you can see a little black box on the video. Keyboard or monitor. What we
All right,
do
we're
is
finished for the
remote-
day,
okay, now
and
turn
it
up-
turned out to be a lot of progress. So we finished the mechanical things, adjusting the motors and encoders, and finally got them talking properly to the software. And I'm going to turn it over to Chuck and let him talk about all the cabling and stuff that was completed.
Well, we had to hook up some of the stuff that we did on the last session in this junction box, and we've now got 3 terminal strips in here, and we're beginning to populate the junction box with a lot of wiring. It's going to get a lot more crowded than it is now before we're done, but we did make progress, and we've got the deck power almost ready to go to plug into the controller.
And then Logan's been working software.
So so my focus has been software, and so I have the controller talking to the computer properly. I have both of the encoders talking to the controller properly, and I loaded the initial setup parameters based off the manual for the scope, and then we actually have the scope talking to Cartesial, which is our pointing software. So that's a big milestone for making all the software work together.
Okay, and so we've got to kind of complete, we've got to bring the power supply to the motors and finish some wiring, but not a whole lot before we're ready to start powering up the motors and actually testing them. And it's all, all of this progress is because I wore my lucky half full shirt, and we had a very optimistic team. And thanks to Mimo, who helped every one of us.
Yeah, so the lesson there is wear the right clothes and you get good results. We're on this.
Okay, well, we've got it tuned sufficiently for slewing right now. It's really not ideal, but I'll show you the motion. So that's counterclockwise and then back clockwise. So we're getting nice smooth motion now in RA, but we have found that it's when we load it with the telescope, we expect we're going to have to retune everything. So this is a great step that we've made today, but it's not over yet. We got to do the deck motor, and then we've got to mount the telescope and balance everything and retune the whole system. But we're looking at light at the end of the tunnel at this point.
That's the back up.
What's that?
Yeah, things like that.
Right. Oh, no, we knew that.
Now the other way,
So
we're
they're
testing
working on the
declination
declination,
axis
and here's
motion.
the
That's excellent.
April
Now
23rd,
the other way,
April 23rd of 2022.
so we're running at 20 volts and with the same settings on the test and tune as we have on RA. That's beautiful. Okay,
In the other direction, it's,
yeah, we may have a little bit of imbalance or something.
it's still.
Okay, now's the day to remove all the temporary stuff. Officially mount it. Then we need to balance it by adding a counterweight on the other side. First counterweight. And then we're adding another. Didn't know if that could be and they're testing.
Okay, we're done for the day, and as you can
Okay.
see, we've got the telescope back on the mount.
Whoops. Okay, and then the final video here is lifting the dome. And may not put it down just a little bit. Yeah, so we lifted the dome by making, actually, the video will play here shortly. Yeah.
Okay, it's a big day today
Okay,
because
no,
we
yeah.
are going to lift the dome to eliminate the interference that we now have between the telescope and the top of the dome. So we're going to lift the dome by, let's see, hand me this foundation over here, slide it over. So this is the new foundation that we're going to put under each drive wheel. So we've got 6 wheels that the dome rests on, and we're going to use scissor jacks and hydraulic jacks to lift the dome by about 5 inches or so, and then we'll slip the new foundations underneath the drive wheels and the idle wheels, all 6 wheels, and then we'll drop the dome back down. So it's a delicate operation, but it should go smoothly. We've done a lot of planning for this, so I hope it doesn't take very long. All right, let's get to it.
There you can see my brother mine in the yellow shirt in the back. There he is. It took a little while at first to at a time. And then put the foundations in, bolted them in place. And we use nylon and finally, we're checking interference. It's just pretty material. I mean, it's pretty. No, it's really good. I've got a few more slides to go through, and I'll just, if you'll advance when I just hit the space bar. So here was the first image. They needed a nice bright target, 9/20, 22, and it was like a year and 10 months from when we disassembled. Next, just hit the space bar. Okay. And then 4 days later, 5 days later, we got M11, the wild duck cluster. Not a great image. Next. Later that night, here's Logan pointing out M11, and you can't really make it out in here, but he's pointing at the pillars of creation there. You can barely see it. Next slide, please. There's Logan and Brennan. I didn't introduce Brennan. He's a UAH student who has been learning to operate. He's almost ready to solo. He's doing quite well. Next. Next. Yeah, so there's the ring. So we're beginning to get a little better images now. Okay, next. And you can see, I see 1296. That is a magnitude 15.4 galaxy off to the side. Surface brightness 23.6.
What kind of duration? Exposure?
I think it's about 20 or 30 seconds a piece.
Yeah, it was like,
I should know it.
yeah, a dozen to 15 exposure. Next.
These are improving as we learn the new system, and we also are doing a bunch of software features. And so that's the reason why these are getting better in quality as time goes on.
And then here we are now in October, the Dumbbell Nebula. Next. M15. This is a stack of 20, 30-second exposures, and you can see even at 30 seconds, we're saturating the center of the cluster because 21 gathers so much light. Next. And M33, Logan, you did this one. You want to say something about it?
So this is fairly bright, well, not a fairly bright galaxy, but a fairly big galaxy in 33. Like it says, stack of 20 images, each one is 30 seconds. And a couple of features, I don't know if can you make out where the dust spots are? And there's one in the right corner. And there's, so you can see
This?
well,
The what?
okay, so
the actual dust spots on the sensor.
Oh,
Bring that
yeah,
up.
yeah.
So one of the
That-
things we haven't
that-
done with some of our processing is that, this is without some of the processing that takes out some of the blemishes. that you
Right,
get
we
in the
need,
real world. So there is a, what those little donuts are actually, little spots of dust that are right on the camera
Mhm.
sensor itself. And then one of the things I'm really proud of in this photo is that there's several, pinkish regions here, and those are age alpha regions inside this galaxy. Which are fairly
Yeah.
hard to get access to.
Yeah, go ahead. This image actually looks better on the computer than it does on the projector. Let's go to the next one. And there's Stefan's quintet, Hickson compacted group. I think the James Webb Telescope did almost as well as this. It was one of the first four images first 5 images they posted. Next. Okay, so okay. So whoops. Our current status is the tracking really is exceptional and way better than what we had. Our pointing accuracy is good, but could be better. We're able to sleuth from target. We don't have a finder camera anymore, a wide angle camera to help us. We don't have to star hop anymore. Sometimes when we slew a long way, we're not on target. Quite often we can see the glow of something on the corner or something like that. Let's see. Yeah, we have work to do, continuing work to do. Hit the next slide. We are seeing some oscillation when we're tracking where stars are like moving about what I think about 3 minutes, I think, of arc, way too much. And we're not sure exactly what that is attributable to. One of the problems we have is that our mount is very stiff in bending, but is not very stiff in torsion. So we're thinking we may have to stiffen it in torsion. Okay, next. Yeah, just keep going. I think I should have. Okay, we did model the mount in software, which means that the software will compensate for any polar misalignment that we have. Yeah, just keep going. Yeah, I mentioned we need to improve torsional stiffness, and we're still working with Chris to improve the PIV settings. And this is much improved as of January 15th, very recently. We need to collimate the optical train. We need to do things like take white frames, stuff like that. We plan to add auto guiding to further improve tracking and sharpen the images. One thing I'm sure you all know, engineers are never finished, but we do make things better. One project at a time. Next. And I think that's it. So thank you. You can take a look at drawings and other stuff that's up here. I did open the observatory. If you want to venture up there, you're welcome to. Thank you so much, Trevor. It's been quite a project, and I gotta say, the team that I've been working with, I don't know, they're kind of a dream team. Everybody brought something unique to the table, but any two of us covered almost any area that we needed. You could take me and Chuck, or Nino and Logan, or just any two of us we were able to do what we needed to do for that day, but each person brought something unique and it's been a great team to work with. And I'm not sad the project's over.
Is there more future? Other than just fine tuning everything or? is there-
It's mostly fine tuning things and taking more images and we do plan to, I've been in touch with Dr. Miller at UAH. He's head of astronomy and physics and he's agreed to meet with me, come take a look and see what our capabilities are. And potentially we'll have some, graduate student, some kind of project that we could do some research with this thing.
You mind if I add to that real quick? Well, one of the things I would say now, for me, as Jeff was talking about, I do maybe the most operations on that telescope. So for me, it's now what I wanted to do is, now the scope is mostly done, I'm wanting to look at optimizing how we take pictures to get the most out of them that we can. So figuring out the best way to do all the post processing, figure out the best way to do the plan, all the observations, all that sort of stuff to get the most out of it.
How about the ability to train other people?
Yeah, so
When's that coming down the pipe?
so Brennan here is relatively new. When did you first show up? It was like October?
I showed up, I think,
I think it's October.
night that you'll have some support.
Yeah.
Yeah.
And then there are 3 other UAA students who have had far lesser involvement than Brennan, but they're still involved.
Jeff, have we done any analysis that says that, there's a threshold where a guide camera can correct for error, and beyond that threshold it can't?
Yes.
Have we done any analysis on what that threshold is? Are we under that threshold now? Are we still above it? Do we need to move quickly to try to refine the amount to get to that much?
That's a great question.